Hello, I am Shane Brinkman Davis Delamore, and this is Code and Optimism, a show where we explore how to solve problems faster with software. This week we're going to do something a little different. We are going to do a live coding exercise. Years ago, I made a video, also on this channel if you look in the history, about how to create a Turing Complete programming language, how to create one in Ruby. It took about 40 minutes. And I thought it might be fun to revisit that and modernize it and update it, and also give a little more context about how I think about these problems these days. Now, why do we care about making a Turing Complete programming language? And it's like, why would you make a new programming language at all? Because programming language is how we express problems to the computer. And I am of the firm belief that there are still huge advantages to be made by making better programming languages. And it also doesn't have to be a great big language that is a general purpose language everybody uses. It can just be a DSL and a domain specific language. And that can really help on certain projects to solve the problem faster. Being able to write a parser for a little DSL or to parse a certain file format faster can really accelerate a project. And there are a lot of tools out there these days that have little DSLs, like Prisma, the database ORM. It's got a little DSL for defining its schema, which is backend agnostic, which is great, works pretty well. And the next question is, why do we care about Turing Completeness? Now, if you know back from your computer science days, Turing Completeness means that any computer or programming language that is Turing Complete can compute anything any other computer or programming language can do. So if we can make a Turing Complete programming language, it can do anything any other computer or programming language can do. It may not be as easy to program, it may not be as efficient, but it can do it. And that's what I want to show today, is it actually isn't that hard to make something that is as powerful as any computer on the planet. And knowing that, having that in your toolbox, can give you a lot of power on projects where it becomes just the right answer to really move things forward. So I'm going to give just a little bit more background on this little project, and then we're going to dive in and do the live coding exercise. So first of all, what does it take to make something that's Turing Complete? Now, broadly speaking, the simple definition is just if you can write a programming language that can itself express a Turing machine, then that programming language is Turing Complete, because Turing machines can be Turing Complete. So without going too much into the details, I'm just going to tell you what we are going to need in our language in order to be able to make a Turing machine within our language. And I'm not going to today show you how to make a Turing machine language we're going to build, but I will link to it in the notes so you can dive in and take a closer look at it. Because really, I think that's actually getting a little esoteric. It's a nice little proof. In practice, what we need is basic math. In fact, we don't actually need to divide, just add, subtract, and multiply is sufficient. But we'll do a little bit more than that when we implement it. We're going to need the sequence of operations, so you can do instructions in an order. We're going to need loops and conditionals. And it turns out a while loop by itself is sufficient because it's both a loop and a conditional branch. And you need an unbounded memory. Now, of course, physical machines in the real world have a fixed size memory, but in principle, that memory could be of unlimited size, and that's what it takes for it to be Turing Complete. Lastly, we're going to use Caffeine-Eight as the language, and we're going to do all this in JavaScript. If I hadn't already said that, I wrote a parser in Ruby called Babel Bridge, and I use this concept, this parsing style called parsing expression grammars, which I like to think of as recursive regex. So if you understand regex and you understand the sense of maybe a regex recursing into another regex, then you'll have a good sense on how you might express things in a parsing expression grammar. That worked really well. That's what I used for the previous video several years ago. Now we're going to use Caffeine-Eight, which is the version that I have adapted into the JavaScript world. It's the version that I used to create CaffeineScript. And it is very similar. There's some little bits of differences. And why is it Caffeine-Eight? Mostly because it's fun, Caffeine-Eight, but also because I wanted to be part of the CaffeineScript suite. So I've got several things that are caffeine, whatever, that really support the CaffeeScript ecosystem. And the 8 kind of aligns with the fact that for parsing expression grammars, there are 8 primary parsing tools. I'm not going to dive into too much here because you're going to see them in the live demo in a moment, but it's matching strings, matching regular expressions, conditionally matching things, not matching things, could matching things, matching things, repetitions of things, or using a rule, which is basically how you recursively match things. And the last is doing a sequence, matching a sequence of things. And those tools, those 8 tools, allow you to express anything you might want to parse. With that, we're going to dive into the live demo right now. Here we go. We're going to need to get our JavaScript environment set up. We are going to use Caffeine-Eight, which is our parser library. The parser library I wrote to support building CaffeeScript. And we're going to use Jest for testing. We're going to have a parser file. And we are going to have a CLI file. And we're going to have some tests. And now, this is our agenda. So we need to create our parser. We're going to add the root rule. Then we're going to do some arithmetics. And then we're going to add memory capabilities and then add while loops. And at that point, we will have a Turing Complete language. But then we're going to continue to a couple bonus things. We're going to add some if rules. So you can have if statements, and we're going to add variables. So let's start with the class. We're going to do Caffeine-Eight.parser. We have to extend that. And that is a parsing class. And we're also going to export this, which will allow us to do tests and things in a moment. We need at least one rule for this to do anything at all. So we're going to start with that. So we're going to say tcparser.rule. And our rule is just going to be the root rule. The first rule has to be the root rule. That's where all parsing starts. And we're going to do a simple rule that just matches a regex, which is a number. And now we should have something that will work. We're going to fill in the CLI here. And we're going to say require tcparser.repl, which uses the JavaScript node built-in command line interactive shell. And so now we should be able to say node source CLI. And now we have an interactive shell, which is provided by the parser. And if I type in something that's wrong, it's going to say parse error, it can't match it. If we type in something right, 1, 2, 3, it says, oh, it found our root. I found our root rule. I found it at offset 0 in the source file, and the string it matched was 1, 2, 3. If I type something else, it'll do it. If I do something like this, where it obviously can match the 89, but it won't know how to do it with a plus yet, it's going to say that it could not match all of the characters. So we're going to take that, and now we're going to proceed. One thing I want to do real quick is let's go ahead and make a script for this, because I think it's going to be handy. Scripts, start, node source CLI. And now we can just do npm start, and it will jump us right into our CLI, which is great. All right, now let's go back, and now we've got the initial root rule. Now we're going to start to do the arithmetic rules. So first thing we're going to do is we're going to add the operand rule for numbers. And we're going to say that root is, except there's one thing that'll match on the root, which is an operand. So we have rules have names. So the root rule can match one pattern, which is the operand rule. And the operand rule can match numbers. And so if we try this, it should work, but it should just be identical. Nothing changed. Well, now we're going to add a new rule, which is a expression. And this expression rule is going to be binary operators. So the operators are going to look like this. It's going to be an operand followed by a, in this case, let's say minus or a plus. Let's put times and divide in there too. And then followed by another operand. And we're going to also say an expression can be just an operand. And then we're going to say that the root matches expressions. So a root can be an expression, and then an expression has two options. The first option is an operand followed by one of these operators followed by an operand. And just in case you're wondering why I had to do the double backslash, it's because the JavaScript will reduce that down to a single backslash, and then the Caffeine-Eight parser will then be able to correctly interpret that single backslash when it's interpreting that regular expression. Now, the alternative is it can be just an operand, in which case it can be a number. So we should be able to do a number or a number plus a number. Let's try it out. Number, great. Number plus a number. Syntax. There we go. Matches number plus a number. So now we have basic arithmetic parsing. We're going to add one more thing to our set of rules, which is going to be an alternative form of operand, which is going to be a parenthetical equation. So we're going to say you can match an expression between two parentheses. Because you will notice, actually, we have not told it that you can do a sequence of calculations like that. 3 plus blank plus 4 plus 5. It says it doesn't know how to do that. But now that we have parentheses, we can put parentheses around them, and then we have an add, and that all parses nicely. So again, this output we're seeing right now is the actual parse tree, and it just tells you the strings that we matched, which is in green here. It also tells you where it matched it in the source, the offset and absolute offset. And then it also is going to tell us that it shows us this nesting. The indentation is the nesting level. Now that is all well and good, but we actually want to get values out rather than just parse trees. So now we're going to shift gears. Let's do one more thing first. If I say this expression, so this works, but if I say it with spaces, it doesn't like it because we're using parsing expression grammars, and those parsing expression grammars explicitly match every single character. And if you don't tell it what to do with a specific kind of character, it doesn't know what to do with it. So we are going to add the capabilities to ignore whitespace. And the rule is I'm going to call the rule underscore, which just makes it really convenient. And it is just one or more white spaces. And now we're going to go and we're going to litter that in a few places where we want to be able to allow white space. So this question mark says it's an optional rule. So this will match one or more white space. And this question mark says optional. So optional, one or more white space. So we're going to put that in all of these, in between all the different parts where we might have it. And I think we'll also put it right at the beginning and at the end of our program. So now if we try that thing again, 3 space plus place, now it parses. Cool. All right. So now we're now to this next part of agenda. Oh, I think actually I want to add tests after we have evaluation. So we're going to get to testing, don't you worry. But now we're going to do evaluation. Let's actually do something with this. So here's what we're going to do. We can add a third parameter to these rules, which is basically a class. This is going to get attached to the node class for this parse node. For any root parse node, we're going to attach the functions for that class. So we're going to define this one function, evaluate. And we're going to return, initially I'm just going to return this real quick just to show you how it works. Evaluate is only special in that the REPL knows what evaluate is. That this REPL that that Caffeine-Eight provides looks to see if you have an evaluate method on your class, and if so, it'll use it. It can be any arbitrary, we can assign any set of arbitrary methods here we want, and when you're doing your own programming language, you probably will assign your own methods for doing different things with your parse tree. But evaluate matches what the REPL expects, and so that's what we're going to use. So now if I type in 1, 2, 3, oh, it evaluates to 1, 2, 3. And if I type in 4, 5, 6, oh, it evaluates to 1, 2, 3, because I told it to always return 1, 2, 3. So now let's fill in the rest of this detail. So what we can do is Caffeine-Eight takes any of our named rules and makes them properties on the current instance node. So I can say this.expression.evaluate. So now I'm going to call evaluate on expression, which down here we can see an expression can be either of these two things. I'm going to cheat just a little bit, and we're going to not do both of them yet. We're just going to do the simple one here. So this second expression is going to match just an operand, and we're going to pass it down. We're going to evaluate the operand, in which case there's two operands. So now let's go in. We're going to fill in just the number operand to start with. So the number operand, what we're going to do is something a little bit different. This.text. So we're going to use JavaScript's eval, which, you know, your mother always told you never use JavaScript's eval, but in this case, it's totally fine because it will only ever be evaluating exactly what this string matches, which is a string of digits, possibly with a minus in front. So it's completely safe, and it does exactly what we want. It's going to parse that number for us, which is great. Now we are going to give that a whirl. Let's see if it works. So now I'm going to type in a different number, and a different number, and a different number, and it works. Of course, now if I do that plus something, it's going to say, oh, there's no evaluate function. And we can go and click on this link, and it's going to say, oh, there was no evaluate function on that expression. That's because we were doing this operation. So now let's fill that one in. We need to put evaluate on pretty much every node here so it works. This one is going to be a little bit different. What we're going to need to do is we're going to take, if there's more than one of the same name, we're going to say left and right. You just put a label in front of it, and now we can reference them by those. So now I can say left.evaluate plus this.right.evaluate. That'll surely work, right? Let's give it a whirl. 2 plus 3 is 5. Great. Now if I say 2 times 4, it's 6. Of course it is, because look, I'm always doing plus, which is not actually what we want. What we want to do is we need to do a lot of different operations. And so we're actually going to do this little trick that I came up with that makes this pretty quick. We're going to eval, again, we're going to evaluate and make ourselves a little function. And our function is going to say A, and then it's going to take, oh, we're going to use another label, the operator here. The operator's text B. And then we're going to apply that. So this is going to evaluate and return us a function that applies whatever our operator is to A and B. And then we're going to apply this to our two nodes. Let's give it a whirl. Oh, op's not defined because op is on this. That's add. Let's do that. And then if we make it to times, it does it. If we say divide, it does it. So that is pretty sweet. All right. So now, as promised, let's get some testing going. It's time to get this going. So we are going to get the TC parser. And let's just do a test. Let's test that the number 1, 2, 3 parses to 1, 2, 3. we're going to expect that tcparser.parse, and we're going to parse the string 123 to equal, and I always like to do sort of a red-green parsing, so I want it to fail first because I want to validate that my test can fail. So it runs it. It says that I did not spell my function name correctly. Let's do it again. Now it says it expected 456, but it got a whole bunch of junk. That's because this is all of the parse nodes. We don't want to do the parse nodes. What we want to do is we want to evaluate. Let's try it one more time. And now it says it expected to get 1, 2, 3 out. Instead, it got the string 4, 5, 6. So that's correct. It should be getting 1, 2, 3 out when we evaluate. And what we're going to do now, we're going to say watch all, and we're also going to get coverage. And so now, look, let's see what we're missing. We're missing line 15 over here. Line 15 is this one. And so that line 15 is actually doing an operand. So before we get much further, what we're going to just be doing all the time is we're going to test parsing a string, evaluating it, and seeing what the results are. So I'm going to do a slightly easier pattern for this. We're going to say const tests, and it's going to be an object. So 1, 2, 3 should be 1, 2, 3. And now what we're going to do is we're going to say for const, I'm going to just call them programs in tests. And we're going to say const expected equals test sub that program. And now we're going to just go ahead and take what we did as a one-off, and now we're going to make it generic. Given a program, and given what we expect is the result, when we parse that program, evaluate it, that's what we expect out the other end. And in fact, that runs great. So now all we need to do is we need to add some type of equation test. And I'm going to again make it wrong to start with. Run it. It says we got 100% coverage, but it didn't match because we expected 10, but we got 9, which is actually the correct answer. So now I set it to 9. Now we have 100% coverage, and we have 100% correctness. So now we can go back to work here. So there's one more rule I did not put in there, which was parentheses. So if I said 4 plus 1 plus 3, in fact, let's do times so that it has to do this. So that should be, 4 times 4 should be 16. So I'm going to, again, make it wrong. And I'm going to run it. And what it's going to actually say is this.write.evaluate is not a function. So this is the left, which is L, and the right, there is no .evaluate for parentheses. Let's solve that problem quick. So here's the parentheses. I put it in. It's an expression. So this.expression.evaluate. And now it worked, but it expected 16. We expected 10, but it was actually 16 because we did red, green. Now it matches, and we have 100% code coverage. And now we have all those current capabilities. There's actually one more parsing thing we're not testing, I believe, which is if we have spaces in our calculation. So I'm just going to put that in. Notice we have 100% code coverage, but we didn't really actually test everything. That is one of the things that you have to be aware of, is that just because you've got code coverage doesn't mean you've tested every scenario. All right, now we really have tested every scenario. So now let's go back to our agenda. Next up, we've added evaluation, we've added tests. Now we're going to add sequences. So we're going to do a little TDD here, and we're going to do the sequences. Sequences means we might want to do more than one statement, one after the other. So I'm going to say 4 semicolon 5. We're going to use semicolons, much like JavaScript. We expect that to be a 5. I know it's going to fail right off the bat, so I'm not going to worry about that. And it says, boom, the parser did not parse everything. It got to 4, and it failed before it got to the semicolon because we didn't tell it how to parse semicolons. Let's do it. All right, so we're going to pass an expression, and then we're going to have extra expressions, which you can have one or more of. So you notice this star and these question marks look a little bit like regex. That's because parsing expression grammars are kind of like recursive regex and use a lot of the same things. White space is ignored here. And these strings are actually names of other rules. But we can also embed actual regex in, which is what we did here. So this can be an expression followed by extra expressions. So now we need to add the rule for extra expressions. tcparser.rule extra expressions. An extra expression looks like this. It is some arbitrary white space followed by semicolon, followed by arbitrary white space, followed by an expression. And that is pretty much it. And we're also going to add, after all this, an optionary semicolon. So you can have a semicolon at the end of everything if you want to. So now that'll parse, but it should now, in fact, it works correctly, but you see what it's doing? It's only evaluating the first expression. So we got 4 semicolon 5. It evaluated 4 and just ignored 5 because we're not actually evaluating this at all. So here's what we're going to do. We want to evaluate that because our tests are still failing. We're going to say last is what I'm going to call this. So what I wanted to do is I have a firm belief that everything should return a value. This is stepping out a little bit beyond what JavaScript does, but certainly what Caffeine-Script and CoffeeScript do and what many other languages do. So if you've got a sequence of statements with semicolons, that is just an expression itself, and the last value in that sequence is what gets returned. So we're just going to evaluate every expression and return the last one. So here's what we do. So if we have extra expressions, this dot extra expression, and I'm going to actually make this non-plural here. You'll see why in just a minute. Non-plural. It's an extra expression is the rule. The extra expression only matches one extra expression. But Caffeine-Eight creates plural versions if there is potentially more than one, in which case there is here. There could be many. So we're going to get an array of them if any match. If none match, there'll be none. So we're going to use the question mark. So now we're going to do for each on this. And we're going to get an expression out of each one if it goes. And if it does, we're going to say last equals expression dot evaluate. And then we're going to turn last. And this should get it. It didn't. Ha! Of course not. So the expression dot evaluate is not a function, right? Because guess what? This doesn't have an evaluation yet, which we can fix quite quickly here. Still doesn't work because of that. Now, if we actually reference the right thing, now we should be assigned to constant variable. Okay, it's not a constant. Thank you. Let. Bam! 100% coverage. Now we have semicolons. Now we've got sequences. Great. Mark that off the list. In order to be Turing complete, the next thing we needed to have is basically an infinite memory. And we're going to make this as simple as possible to start with, which is just one global array that we can store things in wherever we want. So let's do it. tcparser.rule. And this one is going to be, we're going to use the square brackets, much like JavaScript does, but we're not going to use a variable with it. We're just going to use them by themselves, and that's going to access this global array. So open square bracket, optional white space, some expression, which will result in a number, which will then be our index, optional white space, close bracket. And this is going to be the rule for fetching a value. Now, let's go and just copy over one of these things. Now what we're going to do is we're going to take this. So here's what we're going to do. We do need to do expression.evaluate. But we don't actually want to return the index. We want to return the data at the index. And here's how we're going to do it. We're going to put some member functions on parser. So we're going to say get store. And this storage function is going to return this.store if it exists, or it's going to set it this.store an empty array. And so now we can come down here. Oh, that's right. Let's do our TDD here. So we're going to say, well, if we access an array that has not been initialized, then it should return undefined, but it should not fail. Right now, it's going to just fail outright. It's not even going to manage to parse it. So now we're going to go back over here. And, oh, that's right. This rule, we also need to say that this is an operand. All right, there we go. So we're going to say this.parser, because every node has access to the parser.get store. And then we can do expression. Of course, expression isn't accessible by itself. We just say this dot expression. And bam, it returns undefined. All right, that is fetching a memory value. And now we need to set a memory value. And I just copy and paste this. We're going to have arbitrary white space after it. And then it's going to be the equals. And then we're going to have arbitrary white space after that. And then we're going to have another expression, which I'm going to label the second one value. And so it's actually pretty easy, because now we're just going to do this, but do an assignment here. And it's going to be value. I'm not saving this quite yet. So not saved. Let's go do our TDD. Now, if I say 4 equals 5, and then I say fetch 4 back, we expect to get 5 out of it. And right now, it's going to have a parse error, because that equals is not something we've ever understood how to parse before. But now I'm going to save it. And, oh, hi, friends. Look, we're fetching from the wrong slot. Fetch from the right slot, it works. Great. All right, now we got memory. Continuing right along. Let's go and make the while rule. All right, so last but not least, we need to be able to do looping in order to do a Turing complete machine. So tcparser.rule, and this is going to be an expression. And then we're going to, actually I'm wrong, it's going to be an operand. And we're going to say while. In this case, we're going to say required space. So we have to have a space after while. And then we can have a expression. So I'm going to label this test, because we're going to have 2 expressions. And then we're going to have another required space, and then the keyword do, and then another required space, and then another expression. And then we're going to put that in here. Let's do our TDD thing here. And we're going to say that equals 4, and we're going to say while 1. And because we're leveraging on top of JavaScript, 0 is false, non-zero is going to be true. And so it's going to be initially true. And then we're going to say do 1 equals 1 minus 1. And then we expect the result. We're going to write our while loop to return the value of the last iteration. And so the last iteration we expect to be 0, because that's when it should stop. So initially this fails, because it should say, oh, it's missing an evaluate here on the operand. And that's because we don't have an evaluate here. So we actually are parsing it, right? We added the code to parse it. But if I comment this out real quick, it's going to say parse error, right? It's going to say, I don't know what to do with while. And now we say do it, and it's like, great, but there's no evaluate function. So we're going to have the evaluate function, and here's what we're going to do. We're going to say let last, and initially it's going to be undefined if there's no loops. And then we're going to say while this.test.evaluate, and it's just going to be straight out that. That's all we need to do. And then we're going to say last equals this.expression.evaluate. And then we're going to return last. And bam, it works. Beautiful that. Now let's make a slightly more interesting test, because having it just return 0 is a little bit not interesting. So we're going to also do that slot 2 equals 2. And while we decrement 1, we're going to, and look, I'm going to use our sequencing feature, which basically lets me do multiple statements and it returns the last value. We're going to make 2 double each time. And so now it says that fails because it expected the value to be, oh, it had a syntax error. So it had syntax error. That probably means inside our parentheses, we said expression. We don't actually want expression. We want to go all the way back up to the root. All right, I changed the name here, which means this also needs to be root. Bam. All right, so now we have this again returning, which says it received 16, which should be right because we started with 4. In fact, let's bet on this. It should be double that if we make this 4 into a 5, because if 16 at 4, it should be 32 at 5. And it passes the test. All right, continuing right along. And let's pause for just a second to acknowledge that, check this out. We're here. This is Turing Complete. We are at 65 lines of code. But let's continue on. We're going to add if statements and variable rules. And the reason is because even if a language is Turing Complete, it still is not necessarily easy to use. The Turing machine would be extremely impractical to actually program. So we're going to do 2 more things just sort of to show a little bit more what we can do and make this language just a little bit better. So I'm actually going to go copy while, because if looks a lot like while. We've got an if, we've got a test. We're going to use then as the keyword here. And we're going to have an optional else statement. So now we're going to come down here. Let's do this first. So we're going to return this.test.evaluate. And if that's true, then we're going to say this.then.evaluate. If that's false, we're going to say this.else, if it exists, .evaluate. And that is our if statement. And let's go ahead and put in a little test here for it. So we're going to say if, there's something else I want to do too. We're going to put this in here. I want to have comparators. So if for less than 5, then 1 else 2, and I'm going to say 100, just something we know is absolutely wrong. And right now it says compile error because it doesn't know about less than. Let's put it in real quick. So let's come back up here to our operators. I can add less than and greater than really quick like that, and that's it, because the val will automatically work with those. So I put that in, and now I could not find our rule else because there is no else rule yet. Let's add that in. The else rule is going to be quite simple though. In fact, actually we're going to make this even easier on ourselves. So this is the else rule. It's going to be required space, followed by else, followed by required space, followed by an expression. That's it. And we actually don't necessarily need to do an evaluate, because here's what I'm going to do. Look, I'm just going to reach into that else node and grab its expression and evaluate it. That way it saves us a little bit of additional code. So now we have this. Cannot read properties undefined, reading evaluate. Let's make sure I'm looking at the right spot here. Oh, it's not liking then, because then is not right. Ha ha ha. Now it said it received a 1. Great. Let's go see if our test makes sense. So 4 is less than 5. So we do expect to get a 1. And is 4 greater than 5? We would expect to get a 2. Great. While we're at it, let's go ahead and add in the remaining comparators that we might want. And we're going to have to, these ones are pairs, so we have to do them a little bit differently. We're going to say less than equal to, greater than or equal to, equals, does not equals. So now we have all the base operators. Great. All right, we are almost there. We now have if statements. Yeah, let's keep on the 2DD thing. Last but not least, I want variables, folks. So we're going to say fetching a value we expect to be undefined. And it's going to say, don't know how to parse values. No problem. We're going to fix that problem right now. Variables. So tc parser dot rule. We are on the home stretch. This is going to be an operand. And it's going to look like this. It's going to look like a identifier, which we'll fill in just a minute, followed by optional space. Actually, just that's it. It's an identifier because all we're doing is the reading of it. And evaluate is going to look like this. We're going to return this.parser.getContext, which is going to be different from getStore, sub this.tech. I will just identifier identifier.text. Oh, I said identifier. Thank you. This.identifier.text. So we're going to take the text of it, and that's what we're going to look up. Now, we're going to do this, and it's still going to fail because get context does not exist. Oh, there's also not a rule called identifier. Let's get identifier out there. tc parser dot rule dot identifier, and identifier is going to look like this. It's going to be a word. It's going to be word characters, one or more word characters. And now it is saying no get context function. Great. We'll just define that real quick. It looks almost the same as get store, except for we're going to call it context. And it's going to be an object rather than an array. And bang, A is unidentified. Great, let's finish our test. Now we want to assign a value to, and we're going to read it back out. Semicolon, quote. That's what we need. But now it's going to say parser because it doesn't know how to do assignment to a variable. Let's do that quick. We're almost there, folks. Identifier followed by optional space, followed by equals, followed by optional space, followed by an expression. And this is going to just equal this dot expression dot evaluate. And now it's going to say that that is undefined. We expected undefined. Haha. It actually should be 4. So it was working, and we just had our red green going. Now we have 100% code coverage, and we have a lovely little program. So one thing I will toss in here real quick for fun is a little program here that I wrote when I was setting this up, which calculates the Fibonacci sequence. So here it is, folks. So I'm going to restart our interactive, do the editor. I'm going to paste it quick, and then I'll talk through it. So we're going to assign fib. We got a variable to 10. This will find the 10th in the Fibonacci sequence. If fib is less than or equal to 2, then return 1, which is true because the first two values are 1. It's going to track just the last two variables in the sequence, which is the most efficient way to calculate the Fibonacci. And they're going to be 1 and 1 initially. And I is going to be 2, so we're going to be at the now second index. And then it's going to say, is I less than fib, which it is, because our fib, if it was 2, it would have returned 1. So it's greater than 2. So that's going to be true the first time through. We're going to take the temporary value, which is the sum of the last two. We are going to slide the 2 into the 1 slot. We're going to increment I, and we're going to take temp and apply it to fib2, which is the sum of the last two. So basically we just one step up the fib sequence the whole way. And remember, while returns the last value of the statements in its list. And so we should return the last value of fib2 when we finally stop. And we run this thing, and the answer is 55, which happens to be correct. The 10th Fibonacci is 55. We could do the same thing again and do the fib equals 11. And I'm just going to copy and paste the rest of this. And now it's 89. And now last, let's do it one more time to really prove that it is working. If we say fib equals 12, and we paste in that same stuff, we do expect that one to be 55 plus 89, which is 144, which is indeed 144. Great, and we're back, and that's how to do a Turing Complete language. And in fact, not just a Turing Complete language, but one that's actually practically usable. It's like reasonably user-friendly. So again, why would you care about creating a Turing Complete language? And first thing I wanted to show today is that it's actually quite easy to do. You can make a Turing Complete language in parser pretty quickly. And in fact, I don't actually think you need to make a Turing Complete. It could just be the equation parser for doing basic calculations. That can be quite useful in certain projects if it's tuned to whatever you're doing. Also, the parser doesn't have to be big. It can be pretty small. It can be a small little chunk of code that can give you a ton of power. And a small little DSL can be just the magic you need to really accelerate your problem that you're trying to solve. It allows people to express that particular solution, your particular solution, in a way that is natural to the problem domain you're working in. And DSL is, I think, the most useful thing because you're still going to use some mainstream language, JavaScript or whatever, for the bulk of your code, because there's tons of modules out there that can support you getting where you need to go. But then you write your own DSL for that bit that really can leverage something that expresses the problem in the problem domain space that you're talking about. So once again, thank you so much for spending your valuable time with me. I know this episode's a little bit longer, but I hope it was fun. And remember, all problems are solvable with enough knowledge.